Hello everyone, we are going to learn about algebraic structure, groupoid, semigroup and some examples. Algebraic structure. A non-empty set with one or more binary operations defined over it and satisfying certain laws of binary operations is called algebraic structure or an algebraic system. Groupoid. Let G be any non-empty set and star is a binary operation. Then the structure G together with star is called a groupoid or quasi-group if A star B belongs to G for all A B belongs to G. That is, G star is called a quasi-group if G is closed for the binary operation star. If the binary operation star in the set G satisfies the commutative property, that is A star B is equal to B star A for all A B belongs to G, then the structure G star is said to be a commutative groupoid. Examples. The structures N together with addition. N here N is set of natural numbers. N dot, that is set of natural numbers together with binary operation dot. Set of integers together with usual addition. Set of integers with multiplication Z dot Q plus, that is set of rationals together with addition. Q dot R plus R dot C plus C dot are all commutative groupoids, where R is set of real numbers and C is set of complex numbers. The set N of natural numbers is not a groupoid to the operation minus, since if A B belongs to N, then A minus B is not always a natural number. As 2, 3 belongs to N, but 2 minus 3 is equal to minus 1, which does not belong to N. So, minus on N is not closed. Therefore, N together with minus is not a groupoid. So, N minus is not a groupoid. That is, minus is not closed in set of natural numbers. Semigroup. Let G be a non-empty set and star be a binary operation defined on it. Then the structure G star is said to be a semigroup if A star B star C is equal to A star B star C for all A B C belongs to G. That is, the binary operation star is associative. Examples: the structures n plus n dot, z plus z dot, q plus q dot, r plus r dot, c plus c dot are commutative semigroup, where n, z, q, r, c are respectively set of naturals, set of integers, set of rationals, set of reals, and set of complex numbers. The structures z minus, q minus, r minus, c minus are not semigroups, since associativity is not satisfied by these structures. Monoid. Let G be a non-empty set and star be a binary operation defined on it. Then the structure G star is said to be a monoid if the following axioms are satisfied. Number 1. Associative law. A star B star C is equal to A star B star C for all A, B, C belongs to G. Existence of identity. There exists an element denoted by E and called the identity in G such that A star E is equal to E star A is equal to A for all A belongs to G. Examples: the structures Z plus Z dot, Q plus Q dot, R plus R dot, C plus C dot are monoids. The structure N plus is a semigroup but not a monoid, since the additive identity 0 does not exist in N. Theorem. Cancellation laws may not hold in a semigroup. Proof. Consider M the set of all 2 by 2 matrices over integers under matrix multiplication, which forms a semigroup. If we take matrix A is equal to 1 0 0 0, B is equal to 0 0 0 2, C is equal to 0 0 3 0, then A into B is equal to 1 0 0 0 into 0 0 0 B is equal to 0 0 0 0, which is 2 by 2 0 matrix, and A into C is equal to 1 0 0 0 into 0 0 3 0, which is equal to 0 0 0 0. So AB is equal to AC is equal to 0 matrix, but B is not equal to C, since B is equal to 0 0 0 2 and C is equal to 0 0 3 0, which are distinct. Therefore, AB is equal to AC, but B is not equal to C. Therefore, cancellation laws do not hold in the set M. So, cancellation laws may not hold in a semigroup. Set of natural numbers under addition n plus is an example of a semigroup in which cancellation laws hold. Next theorem. A finite semigroup in which cancellation laws hold is a group. Let G is equal to A1, A2, A3 up to An be a finite semigroup of order n in which cancellation laws hold. Let A belongs to G be any element, then by closure property A1, A2, A3 up to An are all elements of G. Suppose any two of these elements are equal. Say A into Ai is equal to A into Aj, for I is not equal to G. Then by cancellation laws Ai is equal to Aj, since cancellation laws hold in this finite semigroup. But Ai is not equal to Aj, for I is not equal to J, as A1, A2, An are all distinct. Hence, no two elements of A1, A2, A3, An can be equal. That is, A1, A2, A3, An are all distinct. Thus, if B belongs to G, be any element, then B is equal to Aai for some I. That is, for AB belongs to G, the equation Ax is equal to B has a solution, which is x is equal to Ai in G. Similarly, the equation y A is equal to B will have a solution in G. G being a semigroup, associativity holds in G. Hence, by theorem, a non-empty set G together with a binary operation or a binary composition star is a group if and only if A star B star C is equal to A star B star C for all A, B, C belongs to G, and for any A, B belongs to G, the equations Ax is equal to B and y A is equal to B have solutions in G. G is a group. Hence, a finite semigroup in which cancellation laws hold is a group, which proves the result.